So, continuing with trigonometry, also know that if, oops, I'll change colors for a second. If this is an angle, and it hits this point on the unit circle, and this is theta, then the coordinate of that point is guaranteed cosine theta, sine theta. That's the other thing about unit circles you have to know. Now, don't just pick a coordinate someplace in space and take the y-coordinate as sine and the x-coordinate as cosine. It has to be a point on a unit circle. All right, so if you remember last thing we ended up with was the pi over 3 breakdown and all the nice algebra that came up with 1/2 square root of 3 over 2 as a point on the unit circle. Remember that? So this is Chapter 2, Section 3. Trig defined on a triangle. And we have to expand it from a unit circle into just right triangle trigonometry. Okay. So here's how I start. I have the right colors here. You start with a unit circle. So I'll draw it in green. So here's 0, 1, and it comes down, and here's 1, 0. I'm just going to do the first quadrant version of the circles. Then I'm going to draw any old circle with any radius. So let's give it a radius of r. So this would be r0. And up here, this would also be 0r. Okay, so far so good? So basically they're called concentric circles. They both have the origin as their center. Then we're going to form some angles out of this mess. So let's have an angle come through here. Some angle. And it hits the unit circle here. And it hits the other circle there. So what I want to do is I want to form right triangles out of this. So I'm going to drop an altitude, and we'll look at this little blue triangle. When it hits the edge of the circle here, it's going to hit a coordinate on a unit circle. So I'll call it, what would be good? Yeah, let's just call it XY. Be done with it. When it hits this point up here, we'll just call it AB. And eventually all these letters are going to go away anyways, and we'll call it something else. So what's the length of the base here? Of that blue triangle? No? To get to x comma y, how far to the right do I have to go? X. And how far up? Y. So this side is x, this side is y. What's the length of the hypotenuse? 1, because it's on a unit circle. All right. Let's form another triangle here. Make it a little bit bigger. Let's drop an altitude from this point down to the x-axis. And we'll talk about this big green triangle. Now, what's the length of the base here, all the way across?
It's x plus whatever.
No, easier. How did I know this length was x? Well, it's because it's below the point xy. So what's the length of this side?
It's a.
It's a. And what's the length of this side?
B.
B. All right. So let me separate my triangles a little bit and have two triangles. Little blue triangle, who has sides x, y, 1, and big green triangle that has sides a, b. What's the hypotenuse?
C squared?
Nope, not in this case. I mean, it's a specific number in this case. Well, not a number, but value. What's the radius of the big black circle, or the big circle?
B radius.
Which is, what did I label it as? See, this was a radius of 1 because it goes through the point 1, 0.
So what would be r?
It would be r, so this side is r. All right,
I guessed on that one. Can you explain it? How does r?
If the distance from the center to the edge of the circle here is r, then the radius is
Okay.
r. Because radius is always the distance from the center to the edge of the circle. All right, so what's true about these two triangles?
They're both right triangles.
They're both right triangles. Give you that. Anything else?
They're proportionate.
They share this common angle down here, theta. So this angle here is theta. This angle here is also theta. Therefore, they are proportionate. That AA rule. Remember geometry?
Yes.
Good old geometry. That the AA rule. That these two triangles are proportionate to one another. So if you zoom in, they look exactly the same, or zoom out, they look exactly the same. So if they're proportionate to each other, what kind of proportions can I set up? Yeah. Pick one. Doesn't matter. X over 1.
Is
X over 1 equals
A over R.
A over R. Okay. Y over 1
B over
equals B over R. Now, if that angle is theta, what's another way of saying X? I mean, X over 1 is just X anyways. So what's another way of saying X in terms of theta? That's when you come back over here. This coordinate here is xy,
That's
but
cosine of
x is cosine of theta. So this says that cosine of theta is equal to the ratio a over r.
theta. Okay.
Y over 1 is the same thing as y, which is the same thing as
Sine of theta.
sine of theta is equal to b over r. Okay. So this allows you to define trigonometry, sine theta and cosine theta, in terms of the ratios of a right triangle. So if this is theta, what we need to do is get rid of the a and the r and the weird letters. So the way we're going to say this is r obviously is called hypotenuse, height. We're going to call b opposite because it's literally across from the angle theta.
Is this gonna be like the tangent and everything?
Uh-huh. And since A is not the hypotenuse, but it's still touching the angle, we're going to call this one adjacent. So another way of writing cosine would be cosine of theta is equal to, well, here's cosine of theta. A is the adjacent side. R is the hypotenuse. So this would be adjacent over hypotenuse as a ratio of the sides of a right triangle. Sine of theta, similarly. The B side we renamed as opposite. So this will be opposite over R, and R is hypotenuse. So this would be opposite over hypotenuse. So it gives us a way of defining sine and cosine based solely on the angle that you're looking at in a right triangle and the sides of the right triangle, specifically two of them. I forgot to define one little thing the other day. If this is cosine theta, sine of theta, there's also a function called tangent of theta. And tangent of theta is literally y over x. Now, whichever triangle you look at, the blue one or the green one, y over x is exactly the same thing. It's opposite over adjacent, opposite over adjacent. So tangent of theta is equal to opposite over adjacent. The sine and cosine generally are the more important of the two functions. Tangent's really good to finding direction. Way of thinking of direction. Now, you have to memorize this. Good luck with that. So, the easiest way I've found to memorize it, I had a teacher that tried to say, oh, it's Sokotoa, the Indian, and I was a horrible speller, so I couldn't spell it out really well. So, in, I think it was 10th grade, I came up with this silly thing. It's still used Sokotoa. And that's the way he tried to do it. So I changed it to a mnemonic.
That's how I learned it.
Sokotoa? I like mine better. Some old hippie caught another hippie tripping on acid.
I remember that too.
Which is really sad because I brought it down to North Carolina and it spread.
Yeah, that's I learned.
The Southern
I learned
hippie?
Sokotoa in high school, and I learned what you just said too.
Isn't that funny? And I found it on our website too. I should have copyrighted it or something, profit off it. So some old hippie, sine equals opposite over hypotenuse, caught another hippie, cosine equals adjacent over hypotenuse, tripping on acid, which is really bad, don't ever do it, is tangent opposite over adjacent. Those 10th grade brains, you know, they're kind of immature. Another one that I heard was something about apples, but I couldn't get it straight either, so
I don't know that one.
I like mine better. All right. And it works rather well.
Might actually easy to remember.
It does. So there's now two things you have to write on a test. One, unit circle. Right underneath it, some old hippie caught another hippie tripping on acid, and that tells you everything you need to know about right triangle trigonometry. You don't need anything else. The unit circle and this take care of 100% of the problems, with some other pictures. So let's look at what we can do now. Oops. The second thing you should do with all trigonometry problems as much as possible is draw a picture. With a picture you can see what's going on and you don't make silly mistakes. So the first thing you should do here is plot 2, 5 someplace. So here's 2, 5. And the angle we're talking about is from 2, 5 to the origin is the terminal side, and the angle formed by the positive x-axis and the terminal side. So we're looking for that angle, or we're not looking for the angle theta, but we're looking for the trigonometry based on that angle theta. So what picture should we draw? Draw a right triangle. So we need to drop an altitude, put the theta in the way, poor guy, and label the sides that we have. How far is the base?
2.
2, because that's the x-coordinate. How far is the height?
5.
5. How do I find the third side? Because we need it for 2 of them, hypotenuse, hypotenuse.
You could do a squared plus b squared equals c squared.
I always reverse it. C squared equals a squared plus b squared.
Isn't it the same thing?
It's the same thing, but the focus on my way of writing it is the hypotenuse. Or if you do AB, it's the focus is on the legs, which aren't that important. So do I know the hypotenuse? Nope, so c squared. So a is going to be 2 squared, b is going to be 5 squared, so that's what, 4 plus 29. So the c equals?
C squared is equal to 29.
Yeah, but c equals?
Square root of 29.
We'll jump right to it. So the radius here, or the hypotenuse, is the square root of 29. And once you have your 3 sides, everything else falls into place. What is the sine of this angle? Which I don't even know what it is, but who cares?
Sine.
The sine.
It's 5 over square root of 29.
Some old hippie. So 5 over the square root of 29. Opposite over the square root of 29. Cosine of theta?
That's 2 over square root of 29.
Adjacent over the square root of 29. Oh, by the way, sometimes you'll see like 5 square roots of 29 over 29. It's the same thing, it's just rationalize the denominator, multiply top and bottom by square root of 29. If you leave it like this, it's fine. I don't mind.
Because that's what it actually is.
Well, it's both of them, they're exact answers. 2 square roots of 29 over 29 is the same thing as 2 over square root of 29. It's just that you can't really have square roots
You're not supposed to leave it there.
Why?
I learned that you're just not supposed to.
Infinite decimals. If you're going to do long division, you'd have to move that decimal over
Definitely.
forever, and you can't do that. So technically, you rationalize. What about tangent of theta?
That's 5 over 2.
5 over 2. Opposite over adjacent. Okay? Good. Let's throw 3 new functions at you. I like building these up as we go. Related to sine is cosecant. And the only thing cosecant does is it takes your fraction and flips it. It is a reciprocal of sine. And the key here also is sine starts with an S, cosecant starts with a C. You never go SSCC. So sine will go to cosecant. Cosecant will take 5 over the square root of 29 and make it square root of 29 over 5. The reciprocal of cosine is the function called secant of theta, which would be the square root of 29 over 2. Now, most people screw this up by going sine to secant, and that's not what happens. It's sine to cosecant. Tangent has its own fancy one. No one messes this one up. It's called cotangent of angle theta, and it's 2 over 5. So far, so good. It's not bad. I mean, once you get some old hippie caught another hippie tripping on acid and you got your order of your angles right in your picture and everything, things usually fall together rather well.
All you gotta do is flip them, right?
All you have to do is flip them. Reciprocal. Reciprocal. Oh, it's horrible. What else? That's not what I wanted. Like this. That's not what I wanted either. Oh well. Alright, so that's the right triangle definition of sine, cosine, tangent, and the cosecant, secant, cotangent. Couple other weird things. While we're talking, I can deal with that later. Special triangles. Star, you're going to live by these. Most problems come back to these in some fashion or form. So to construct the special triangles, just in case you forget how to do it, one of them, you draw off an equilateral triangle. What's true about equilateral triangles?
All the sides are the same.
All sides are exactly the same,
And all the angles are
and all the angles are exactly the same. What's the measure of the angles?
60.
60, because it's 360. It's 180 divided by 3. So this angle here is 60 degrees. And what I'm going to do is give each side a length of 2. But I'm only going to label the top 2. This is just in case you forget what the drawing is all about. So you start off with an equilateral triangle, give the sides of the triangle 2, the angles are automatically 60, and drop an altitude. What does an altitude do in an isosceles triangle?
No, it's not so.
Or equilateral, it does it to both.
I know that
When
takes
you-
right angles.
Well, it comes at right angles because it is an altitude. What else does it do?
It flips them.
Does it do anything to the base?
It cuts it in half because it's
Cuts it directly in half. So the length of this side over here is 1. So you get this right triangle here, and I usually draw it lined out this way, where this side is 2, the hypotenuse. That's this side over here. And this side is 1, which is the base right
this
there.
one, so you have to find the other side.
How do you find the third side? Pythagorean theorem. 2 squared is?
4.
Take away 1,
It's 3.
square root it, and it becomes the square root of 3. This up here is 60 degrees. Well, if this is 60 degrees and this is 90 degrees, what else does an altitude do to a triangle?
Makes it
Well, it takes the angle up top and bisects it.
It makes it 30.
It makes it 30. So this is known as a 30, 60, 90 triangle. You need to memorize this picture. So on test day, the first thing you do is you draw your unit circle, you put it right down some old hippie, and you draw that triangle. So this is one major picture you need. Why? Well, what's the sine of 30? Sine of 30 degrees. Unlike over there where it was sine of theta, I have no idea what the angle is, but I can find the ratio. Here I have sine of the angle, and I can find the ratio by this special triangle. So sine of 30 degrees would be opposite, 1, over hypotenuse, 2. So this would be 1/2. What about tangent of 60? Now this is where your eyes will trick you, so you have to be a little careful. 60 is this angle up here. All the sides change names except for the hypotenuse. The hypotenuse is still 2, but according to 60,
Square root of 3 over 1.
opposite is square root of 3, and adjacent is 1. So it all depends on what angle you're touching is your adjacent. So tangent is always opposite over adjacent, tripping on acid. So opposite is square root of 3, adjacent is 1, so the answer is square root of 3. So tangent is 60 to square root of 3. So this tells us specifically angle relationships and ratio relationships, which is kind of nice. The other special triangle is actually, I think, easier. We start off with a square. You label each side of the square 1. Squares have all right angles, all exactly the same sides. And you draw in a diagonal. What does a diagonal of a square do? Take a guess. Pretty much what happened over there. Doesn't bisect a side.
It cuts in half.
Cuts what in half? The only thing that's cutting in half is not a side, so it must be.
It's the hypotenuse.
What else got cut in half besides the side over here in the
The degrees.
the angle, right?
Yeah, it's
So this
45.
angle gets cut,
Makes it 45.
makes it 45. So when we do this diagonal of a square, and we leave these sides 1 and 1, this angle becomes 45 degrees, and so does this. So this is known as a 45, 45, 90 triangle. What's the third side, the hypotenuse?
1.
1 squared plus 1 squared is?
Wait,
1 squared
I'm
plus
thinking
1 squared
It's 2.
is 2. Square root it, and you get the square root of 2. So that gives us another special triangle. So if you ask something like, what's cosine of 45 degrees? The answer is, well, you go to 45 degrees, actually either one of them, it really doesn't matter. And cosine is some old hippie caught another hippie, AH. So cosine of the 45 degree angle here would be adjacent over hypotenuse. So it would be 1 over square root of 2. Now the book is not going to write it that way. The book is going to write it square root of 2 over 2, which is exactly the same thing, just rationalized. Multiply top and bottom by the square root of 2. All right, here's the important one. What's the tangent of 45? Tangent is tripping on acid. So if I'm looking at either of the 45s, it's going to be opposite over adjacent or opposite over adjacent, which is 1 over 1, which is 1. This is the one you use to make sure your calculator is in degree mode. If you type in tangent 45 and hit enter, the answer should be 1. If it's anything else, you're in radian mode. Now, some problems you want to be in degree mode, but some problems you also want to be in radian mode, so be careful.
If you're in radian, how do you change it?
On that calculator, there's a degree button up top.
So you said if I hit tangent of 45?
Yeah, if you hit tangent of 45, it should be 1.
Okay.
Your calculator's standard in degrees. Now, if you want radians, go up to where it says DEG or DG.
DRG?
DRG. Hit that.
Oh, radian.
And
What is a GRD?
Gradient. It's something else. It cuts the top half of the circle to 100 degrees.
Okay.
Go figure. I never could figure that out. So, with these two triangles, we can do at least a couple angles, 45, 30, 60. Do not use these for 90 or 0 or 180 because you need the unit circle for that. You have to go back to the unit circle. So far, so good? It's not bad. It's not bad. But if you get this stuff down, then the rest of it actually becomes a lot easier. I'll leave them there for a second. Just not in the video. Let's see here. Blah, 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 blah. Covered all that. Oh, we'll talk about that in a second. And we can do a couple of those. All right, let's talk about the cofunction identity. Now the cofunction literally is you have sine on one side and cosine on the other. So sine and cosine are called cofunctions of each other. Sine and cosine are cofunctions of each other. Same thing happens with secant and cosecant. There's a relationship between those two functions. They're not reciprocals. Remember, sine and cosecant are reciprocals. So secant and cosecant have a different relationship. And the same thing happens with tangent and cotangent. There's a special relationship between them. Okay. Get rid of these anyways. Ah, that black mark is horrible. And this is how we figure it out. You draw a triangle, right triangle, and you label this angle alpha, and you label this angle beta. Greek letter time. And let's say this side is A, this side is little b, this side is little c. Right. So this is an angle, this is an angle. Angles always go inside a triangle. Sides always go on the outside. Please don't get those confused. Well, one thing I forgot to mention. If I take sine of something and it's equal to something, what is a sine of? What kind of value has to go inside those parentheses? What do we call it? The sine of?
Sorry, what? I was writing down. I'm not sure what you said.
What did you say? You're mumbling. Great.
What did you say?
I said, if I'm taking the sine of something, what does that something have to be?
A degree.
What are degrees usually called? What do they measure? What do degrees measure? What do radians measure?
Pi.
What's the point of them? If I asked you to draw 30 degrees, how would you draw it?
You draw a picture.
And what would the picture...
Angles.
Thank you. All right. So the sine takes a angle. You cannot put ratios in there. They have to be angles. 30 degrees, 2 pi over 5, you know, some kind of angle measurement. What's it spit out?
A number.
What do we call
It's a
numbers
ratio.
like a over c?
A ratio.
Ratio. So whenever you're working with ratio, with sine, cosine, tangent, whatever it is, it's always the function is taking an angle and spitting back a ratio. Ratios are generally written as fractions, but they don't always have to be. But the angle's the important part, because later we're going to undo it, and if you don't remember what's what, it gets very confusing. All right, so let's look at this. Can you tell me what this is equal to?
Oh.
That's alpha and beta, not A and B.
Yeah, I was about to say C. I saw the B and I was like, oh, C.
This is the angle, the measure of angle alpha plus the measure of angle beta is equal to?
This is going to be 180 minus 90, so it's going to be 90.
It's going to be 90 degrees. The acute angles of a right triangle are complementary. Back to geometry. Didn't you love geometry?
No.
That a terrible teacher.
Oh, I was a terrible teacher too. All right. So also I could write this as beta is equal to 90 degrees minus alpha. That's legal, right?
Sorry. Yes.
I just, subtract alpha from both sides. Okay. So tell me this. What is the sine of alpha equal to in ratio form? The sine of alpha, which is this angle over here,
It's
some old hippie.
it's A over C.
It's opposite over hypotenuse, so this would be A over C. What is cosine of beta equal to? Now beta, be careful, is the angle up here.
It's still A over C.
It's still going to be A over C because from beta's perspective, A is adjacent and C is hypotenuse. So it'll still be A over C.
So A over C is going to be the sine of that degree, but also the cosine of the other one.
And that's why they're called cofunctions. So I know for sure now that sine of alpha is equal to cosine of beta because they both share a common ratio. And therefore I can set them equal to each other. But then I can do this little substitution. I know beta is equal to 90 minus alpha. So I can say that sine of alpha is equal to cosine of 90 degrees minus the same angle alpha. And that way you get a formula in terms of one angle. And that's what it means to be a cofunction. So you can do that with secant, cosecant, tangent, and cotangent.
Now, how would you solve that?
Well, if you have the sine of 20 degrees, that's the same thing as the cosine of
So,
70 degrees. So depending on which one you want,
I'm saying, like, could you solve it without knowing what the alpha actually is? Like,
No.
you're trying to solve for
I need
alpha.
a ratio
You
of a
need an
triangle.
actual number.
Yeah, I need triangle.
Okay.
The ratios are going to be the same, but the angles are going to be complementary. So finding the sine of 20 degrees is the same thing as finding the cosine of 70 degrees. So if I tell you that the sine of alpha is equal to 1 over 5, then the cosine of what is equal to 1 over 5?
It's the cosine of
Well, what's the relationship? If this is alpha, what does this one have to be for them to be the same? No.
I thought it was the same thing.
No.
But there's a sine of
The sine of 20 is the same as cosine of 70. So the sine of alpha is going to be the same thing as cosine of 90 minus alpha. If they're both equal to the same ratio, that means they have to have complementary angle relationship. Is that useful now? Not really. Later? Yeah. We're going to do a lot of cofunctions later on. And they do come in handy for higher math. But for our purposes, not super important yet. Oh, by the way, I didn't erase it over there yet. You can also write this sine of alpha is equal to cosine of pi over 2 minus alpha. That's another possibility.
because power 2 is 90.
Pi over 2 is 90 degrees, depending on if you want degree mode or radian mode in your math.
Which one would you recommend as a degree?
If you want to get to calculus, radians. And there's a reason. Calculus is defined using radians, so if you try to do calculus in degrees, you actually have to do more work. And you don't want to do more work. Let's talk about applications. What time is it? Since we were all late, I'm a little bit off time. 20 minutes. 20 minutes?
It's 2:20 right now.
I get until 3, so I got more than 20. I got 40 minutes. Yes. I'll be done before that. Because missing half the class throws me off.
They missed 10 minutes.
No, half the class. The other 3.
I thought you hit like half the class period. I was like,
Let's talk about line of sight. This is one of my funnier pictures. The eye of Ra.
Awesome.
Let's give it some eyelashes. And now it looks like an amoeba. Amoeba. Or I can say that word. All right, so line of sight is straight ahead. Literally. You're not looking up, you're not looking down, you are looking parallel to the ground. Not very many people do that. Most people look a little bit down because they want to see where the heck they're going. All right, if there is an airplane up here in the sky, a horrible drawer.
Oh, is this gonna be like one of those, if we have like a word problem or something?
Uh-huh.
Yeah, I remember this. I remember line of sight.
Yeah. So if you have line of sight and you look up at an airplane in the sky, then this is called the angle of elevation. The angle off of your line of sight up to the object in the sky is the angle of elevation. If you're looking at a bug on the ground, I'm not even going to try to draw it.
Just right bug.
Little ant.
You could have drew like a spider, a little body with legs.
Little legs there. There we go. Look at an ant on the ground. Then you would look down at the object, and this would be called the, well, that one would go that direction, that one would come down. Angle
Is it
of depression.
I knew it. I didn't want to say depression. I thought it was wrong.
Sounds very depressing.
Exactly, that's why I didn't say it.
So using these two types of angles, we can construct triangles. I mean, they're staring you in the face. Here's one triangle, and here's the other triangle.
The problem's going to tell you like how high or how low it is, right, from your line of sight.
The angle, yeah. And then you usually have to
It's
find
gonna
out how
tell you
high
the
and how
angle.
low it is. It'll tell you the angle.
So instead of telling you how high the plane is, it'll just tell you the angle of where you see it.
And you find how high the plane is.
It's not that hard.
No, it's not. It's actually kind of easy. But I've had people screw it up before because they draw their pictures awkwardly. I remember in high school once, I had a kid flying a kite. It was on a test, you know. Kid's flying a kite. The kite has a string of 150 feet. So they drew their pictures like this. Here's a kid. He's flying this kite, 150 feet. What's wrong with that picture?
Kites never fly straight up in the air.
Kites never fly. I guess they've never flown a kite before.
I never have either.
Ah, but that just doesn't make sense because it would just.
They see it on the.
I know, but I had people drawing that, and therefore you don't get a triangle, and therefore you can't find anything out about it. Oh well.
So was the 150 inches supposed to be
Feet.
Was it supposed to be the hypotenuse of the triangle?
Uh-huh.
Gotcha.
Yeah. So it depends on how you draw your picture. If you draw your picture wrong, well, yeah, this is going to get all screwed up. So, for example, I'm just going to draw a picture. Here's Joe Schmo. He's standing on the ground. Here's a building. Little door, some windows. It's the new building they're constructing
That's
over
my
there.
house.
It's your house, 3 stories high.
I'm looking at it. Yeah.
And what you want to do is you want to find out how tall this building is. So you keep your line of sight, staring right at the building, and you can get a device. It's not really hard. You can actually construct one on your own. Get a protractor, you know, the rounded angle measures. You attach a string to the center of it so that when the angle is held horizontal or parallel to the ground, the measure of the angle would be 90 degrees. And then you can lean it up and sight where you're looking at the top of the building and look at what the angle is that measures it. Does that make sense?
I would have to see it.
You'd have your protractor and you're looking up at the building this direction. And this would be if the string was hanging with you holding it parallel to the ground, so it would look at 90 degrees. And then if you're looking up the building, the string's going to fall here.
And
So
it's going to move the thing in the middle.
Yeah.
So the angle is.
So that would be the angle of elevation.
I would still have to see it though. Like, I'd have to see someone do
You'd
it.
have to pull it off to the side to look at it. But it would be like, say, if it hit 30 here on the protractor, then the angle of elevation would be 60 degrees. Because the measure of angle between 90 and 30 is
Okay.
60.
Okay.
So the string swung 60
I thought you were
degrees.
saying that it had moved to like if it had if it was 30 instead of.
Well, on a protractor, zero's over here. So you kind of have to reverse engineer it. Be nice if it was 0 there and measured backwards. But you can design something so you can look up at a building. You can measure this angle of elevation. Let's say theta here equals
30 degrees.
28 degrees. How boring. Why would I want to do 30? I could do a special triangle then.
Because it's easy.
Yeah, I know. So I'm going to do 28. The only thing else other than measuring the angle of elevation is you have to know how far away from the building you are, from the base of it backwards. So let's say we are 100 feet away.
Whoa.
So we're backing up 100 feet, we're looking up at the top of the building, we're measuring the angle. So this will find this side. What other piece of information do I need to know?
What the angle of the other side?
Mm-mm. I can find that, that's easy.
The hypotenuse.
Mm-mm. If you want to know the height of the building, you have to know this height.
Oh, yeah.
Because you're standing there holding it up, and I'm about 6 foot, so that would be 6 feet extra that I'd have to add onto the building. So let's say this is 6 foot.
Would it tell you that?
Yeah, it'll say the person's 6 foot holding onto this thing, measuring. Most problems don't even worry about that; they just drop it. They make the person's head here, which is kind of
Okay.
silly. But
Is that how you're going to do it? Or are you
Either
going
or.
to do it like that?
either or, you have to be careful. But I have to tell you what that distance is. So if I don't tell you, then you can say you don't care about it.
Ground level.
Yeah, you're at ground level. But if I do put it in there, you have to add that to your answer. Because it'll be x plus that 6 feet here at the bottom. All right, so what function is going to help me find x? Well, your concentration should be on your angle and labeling your sides. What is the x side called in that triangle?
The x.
Yeah.
That's the opposite side.
That's the opposite side. So from 28, x is the opposite. What's the other side I know?
The adjacent.
The adjacent. So what function deals with opposite and adjacent?
It's a cosine. So I'm looking. Oh, sorry. It's
Tangent. Tangent is, you know, the TOA. I don't know what the heck I just wrote. TOA. Tricky on acid. So you're going to say tangent of something is equal to something. Well, what does the of something have to be no matter what? It has to be the angle. So the angle here is 28 degrees. And what it's equal to is the ratio of opposite over adjacent. Opposite is?
x plus 6.
Don't put that in the triangle because x plus 6, that takes you outside of that right triangle.
Oh, so you're adding 6 at the very end when you find
To your
out.
answer, yeah.
Okay.
So it'd be x over
100.
100, and then solve for x. So you multiply both sides by 100, and you get x is equal to 100 times tangent of 28. Thank God for calculators.
That is approximately 53.17.
Yeah. The only thing is your calculator, its standard mode is radians. Do you know how to switch it?
Mhm.
Okay.
It's approximately 53.17, so 53.
No, that's just x, right?
Yeah.
Okay. So x is 53 feet,
Yes.
and then we have to add on the 6-foot person, so it's
59.
59 feet tall. Sounds about right.
Has it
3-story building, about 59.
Yeah.
That's it. It's all you have to figure out is how tall the building is. So this building is, from top to bottom, 59 feet. And that's the power of trig. You can measure things that you cannot normally measure. It allows you to measure things that you normally cannot measure. For instance, another little example, just a baby one.
I have a question.
Mm-hmm.
You said you get partial credit for showing work, right?
Mhm.
If we did it like all the work, but we had drawn a picture wrong, yeah, and got the wrong answer because we just drew the picture wrong, but we did the correct work.
Then I'd grade the work as partial credit, and the picture I'd kill you on. Because the picture should be the easiest part. Let's say you have a lake. It's a rather large lake, and you want to know how far it is from here to here. Like you want to canoe across it or something.
Okay.
So you're standing over here. I'll put my little stick figure. You're standing on this side of the lake. And what you do is you find a landmark on the other side, some big tree, I guess, would probably be a good thing to look at. And you use that as your line of sight. So you're looking straight ahead at that tree right there. And that's the distance you're curious about, so let's label it D. And then what you do is you walk away, but you have to walk away in such a way that this is a right angle. All right? Later, we don't have to walk at right angles. We can walk away any which direction, which is kind of cool. But right now, we have to go right angles. Say we also did this at 100 feet. And you have to look back at the same landmark, that tree over there, and measure the angle from where you were, put a flag or something, and the tree. Kind of like surveyors. You know the surveyors with the sticks.
Mm-hmm.
That's all they'd use is trigonometry to define how high the road is moved from one distance to another, how far apart they are, everything, angle of elevation. They do all those calculations. And again, the famous function that gets used is, if I know this angle is, what would be a good one? 78 degrees, almost 80 degrees. Then how do I label the sides that are of interest? In other words, if this is 78 degrees, what is 100 called? Adjacent side. What is the distance called? The opposite side. So what function is adjacent and opposite? Opposite and adjacent is a tangent. Okay, same function. So you go tangent of 78 degrees is equal to opposite over adjacent, so it would be d over 100. And you get d is equal to 100 times tangent of 78 degrees.
It's approximately 470.4. So 470.
470.4 feet.
Why did you go 470?
What did you say?
470.
70. 470.4
Yeah.
feet. So the distance across this lake would be 470 feet, but you never even traveled that 470 feet, you just measured it on one side of the lake. Measuring the distance across a river is best for this because you don't want to cross the river, you just want to know what the distance is. Alright, so most functions you'll find of that situation are tangent, but they're not always tangent. So you have to be kind of careful. Let's go back to my boy with a kite. Words. From words, picture. So what should you start with for your picture?
Draw a person. Flying.
And while we're drawing the person, what else?
How high the kite too.
So you're going to have this guy kind of hanging out here, and then string straight up?
No.
No. String somehow out.
Just going out somewhere.
Now, one of the things we're ignoring here is with physics, if you have a string even as tight as possible between 2 points, it always has a little bow to it. So we're assuming that this is a straight string. It's impossible to do, but it'll still be pretty close. And we'll have a kite
Is
here.
it really impossible?
Yeah.
How is it impossible?
Because gravity's pulling down on the string all the time, so it loops.
No matter what.
No matter how tight you make it,
it's always going to be a little
A
curve.
slight bow to it.
That's cool.
It is kind of cool. So here's my kite, you know, the little tail, all that fun stuff. What else should I really draw?
You need the line of sight.
You can either do the line of sight. I didn't tell you about the boy's height, so I guess we're not worried about
So
that.
that's just going to be at 0.
So here's my line of sight, right off his hand. Okay. I personally would have drawn the ground, but that's just me. I don't want the boy falling, you know, to the center of the earth. All right, and then this angle here is what we're talking about. It is the angle of elevation that the string makes with the ground is 25 degrees. So here's 25 degrees. What am I interested in?
How high the kite is.
How high the kite is. So go to the kite and do
Kite
what?
Going down.
Perpendicular, I would hope you mean.
Same thing.
Right angles, altitude, literally altitude. All right, what else do I know about this picture?
The hypotenuse is 150.
And the hypotenuse is 150 feet. So we're looking for, I'm going to label this y.
Okay.
Probably should have labeled that y also, but So what function has an angle here? What is this side y called?
It's opposite.
Opposite? 150 definitely is.
Hypotenuse.
Hypotenuse. So what is opposite and hypotenuse?
Sine.
Sine. Some old hippie. So you set this up as a sine function. So you go sine of 25 degrees is equal to opposite over hypotenuse. So it's all determined on where the angles is and what sides you're interested in, have or are interested in. So multiply both sides by 150 and you get 150
It's
sine of 25 degrees, which is approximately
63.4.
63.4 feet. So that flat kite, I said flag, that kite is 63.4 feet high. Plus whatever the boy's, how high the off the ground, the boy's holding it, but I didn't tell you that. He can't be too tall, maybe 3 feet off the ground.
That's a small boy.
Yeah. Well, I mean, when you hold a kite, you don't hold a kite at your head level, you hold it at your waist level.
I've never flown a kite.
You never flown a kite?
No.
Oh, that's so sad. I had a triple kite once where you can turn it and make it do loop-de-loops and stuff. And I always found the string kind of tangled in on itself, so I have to look at that. I guess there's a way of counting how many loops it does, so then you unloop it the other way. But I never got into that.
It's probably all math.
You've never done a kite, that's just... I guess because there's so too many darn big trees around this place.
Oh, the house that we used to live at, I lived there for 14 years. It was surrounded by trees.
Well, I've never flown a kite in a yard or a house, always a field or the ocean.
Well, we
Or
lived
lake.
in the middle of a cotton field, but I mean, it was still surrounded by trees, though.
Yeah.
Like, there's no possible way to fly a kite without getting caught in the tree.
It's so sad. We should have a project, fly a kite project.
And then we measured the angle
And then you can see when you look at the string going to the kite, it always does that. It's kind of weird. It's flat along the horizon, and then it suddenly goes up.
Well, that's because the wind is carrying it, and with
Well,
gravity pulling it down. But what if we had 2 people really pulling the string as tight as they can?
Still would have a bow to it.
So if we were at ground level and 2 people pulled the string, as
You could
far
take
as
a
they
fence
could-
post and put it on both sides and have a winch to tighten it.
Mhm.
And as you tighten it, there always, might not be able to see it, but there's always a slight down to it because of gravity. No matter what, how tight you can get, it doesn't matter. All right. One of the ones that is hard to do is a word problem, but I still want to talk about it. Let's move the triangle weirdly. Doesn't matter what way the triangle is drawn, as long as you know where the right angle is. Because once you know where the right angle is, opposite is the hypotenuse. And that should be the first side you always find. So if I tell you that this side is 20 degrees, or I'm sorry, this angle is 20 degrees, and the hypotenuse is, no, hypotenuse is what I'm looking for, so let's label that H. And opposite is 38 feet. What function would I use? And then solve. So you start with the angle. That forces that side to be opposite, and we're looking for the opposite side of the right angle, so that's hypotenuse. So opposite and hypotenuse is what function? Sine. So you start off with sine of the angle is equal to opposite, which is 38, over hypotenuse, which I'm just going to call h for hypotenuse anyways.
So you get to do 38 divided by sine of 20.
Right. How'd you just figure that out so quick? Just curious.
Really?
Yeah, I just want to know what math allows you to do that.
I really don't know what it's called, but I just know from
Anyone?
past experience
That you just flip them.
that whenever it's a fraction, the top number is always the answer by itself multiplied by the denominator.
What's this called? Do you remember? It begins with a P. We used it for the triangles.
Can you give us another letter?
We used it for the
PR?
PR,
Another hint?
PRO.
Proportion.
Proportionate. Or in proportion, kind of like the triangles. So what allows you to take the top and the bottom here is this is a proportion, sine of 20 over 1, 38 over h. And with proportions, since you cross multiply, the order of the cross multiplication doesn't matter. It doesn't matter if it's a times d or d times a. So you can take the diagonals and switch them if you want. So you can write this as d over b is equal to c over a, and it's still a proportion. So the trick you're using is proportionate.
Oh.
So when you flip these two, it becomes h is equal to 38 over the sine of 20. I hate doing things in math if you can't prove it.
I just do it because from
I know,
past
because it
experience.
works.
Yes.
And when you solve it, that's what it looks like.
It makes it to where if you multiply the denominator by the
I like
answer by
having
itself.
reasons why it works, as otherwise I don't like using it. All right, so what's 38 divided by the sine of 20?
It's approximately 111.1.
1,
0.1.
1, how boring, feet. So the hypotenuse would be 111.1 feet. So that's only setup that I worry about is I have people setting this up this way, and then they multiply both sides by 38 and do 38 sine of 20 like the other ones were. But this one you have to be careful, the h being in the bottom will throw you. So just do the diagonal switch and you're pretty safe. I think that's it. Ooh, I do want to do one more problem. Do I have enough room? I should have enough room.
It's a sand castle.
Castle.
Made out of sand.
Well, no, this is a real castle.
Why not?
Yeah. Let's make the height of the wall 75 feet. That's a really tall castle, by the way. Most castle walls are about 30.
It's King Arthur's castle.
And this is beyond King Arthur's castle. This
It's
is
King Arthur's granddad.
one of those fantasy ones. So you have a castle up here. You have a guard up here. He's, you know, keeping out track. And he has a sword and everything. Have fun
And it's
with
on
these
fire
drawings.
too.
Oh, that would be awesome. And he notices in the distance that there's war engines coming. A little catapult.
No, it's a tank. It's a
No,
modern
this
day
is a
tank.
castle, there's no
It's a modern
tanks.
day tank.
So there's this catapult coming, and he wants to know how far away from the castle it is. So the castle is 75 feet. Line of sight is this way, above everything, right? And he's going to look down on the catapult in a distance. So he's going to look down at 7 degrees. So he looks down just a little bit and he sees this catapult coming up and going, oh, run for the hills. Attila the Hun is coming. So what he wants to do is he wants to be able to report how far away that catapult is. So what triangle would you set up? The top one or the bottom one?
The bottom one.
You would think picking the bottom one. The problem with the bottom one is, if this was a word problem, I would say the angle of depression is 7 degrees to the catapult.
Well, you can't do the top one because when you get the...
Well, I know, you can do the top one. But this is my warning. I'll have this all in words, and people will put 7 degrees here. Because they see the angle of depression, and they think, you know, from the catapult to the castle, which is ridiculous. So what I suggest is you do this. Little geometry. These are parallel lines, the top line here and the ground there. This is called a transversal. Remember transversals? Geometry? This angle and this angle are considered, why? What do they
They're
call
the
them?
opposite sides of the transversal.
What do they
I don't know what it's called, I just
No.
know, okay?
Do you know? Brinkley, do you know the name of the angles? One here and one here?
I just can't remember.
They're opposite, I'll give you that. They're alternate. Oh,
Give
come on,
us a
geometry.
Give us a letter.
Alternate interior angles.
Oh, okay.
Alternate interior angles. So this angle and this angle are exactly the same. So here's the cool thing. The angle of depression is exactly the same as the angle of elevation, depending on your perspective. So from the guard's perspective, his angle of depression to the cart is 7 degrees. From the cart's or the catapult's perspective, it's a 7-degree angle of elevation to the guard. So it's always going to be equal. Angle of elevation and angle of depression are equal on opposite sides of the observation. So I would pick the triangle here and make this 7 degrees. You could draw a perpendicular next to the catapult and use the top triangle also. I think that personally is safer, but oh well. So what do I have? Well, I have 7 degrees here. I have a 75-foot castle, and I want to know how far away this guy is from the castle. So I can report it to my king and say, listen, buddy, we're going to die soon.
It's King Arthur, you will never die.
So I'm looking for this distance. So what relationship do 7 degrees have with the 75 feet?
It's the opposite.
Opposite, and D is
Jason.
adjacent. So we're back to opposite adjacent. What function is that?
Tangent.
Tangent. So we go tangent of 7 degrees is equal to opposite, which is 75, over adjacent, which is the distance I'm curious about. And the trick here is to use that proportionate diagonal and flip the two sides. The D replacing the tangent replacing the D. So the distance here will be 75 feet divided by tangent of 7 degrees.
Which is approximately 610.8.
Feet. Maybe I should have made that in miles. Yeah. Meters? Meters. Yeah. He's pretty close. He's going to
You
start
can go
bombarding
ahead and
us.
sit there and shoot the catapult out.
I should have made the angle like 1 degree or something. It would push him further away. All right, so that is trigonometry on a right triangle. Oh, except for